Okay, so there's these implicit curves can be interesting from an engineering point of view, but there's something else that implicit differentiation does, and what it is it allows us to differentiate what are called inverse functions. So for example, inverse sine, inverse tan. Log x is the inverse of e to the x. It allows us to differentiate that. It actually allows us to differentiate square root, which is the function, is the inverse of squaring. Implicit differentiation allows us to do this. And basically the idea is, if you've got some function of x, which you do know how to differentiate, if you apply the inverse of f to both sides, you get f inverse of y is equal to x. And then what you can do is you can differentiate both sides with respect to, I'm possibly not doing this exactly right, it should be starting the x and y's mixed up. It doesn't matter, we'll see it in examples. Differentiate this implicitly and you end up with an equation of x, y and dy dx, and you can solve for dy dx in terms of x and y, and usually the original y was in terms of x, so this is kind of how this works. So actually I've said it exactly wrong. If you want to differentiate a function and you know how to differentiate its inverse, you can do this thing and then do implicit differentiation. So we'll see two examples. This is the other type of question that I ask in this thing. Okay, so what I got here, there's a bit of spiel. The exponential function f of x equal to e to the x can be defined as the solution of the ordinary differential equation. So this is saying actually this is a defining property of the exponential function. If you differentiate it, you get the same thing. It is its own derivative and it's 0 to equal 1. That actually specifies the exponential function uniquely. The natural log ln of x is defined as the inverse of this. So what that means, by the way, is we'll do just one example. And you can do it for any number you want, really. So we said that e to the 0 is equal to 1. So you can draw this like this. This would be the exponential function. E to the 0 is equal to 1. Well, natural log is the inverse. It'll bring you backwards. ln of 1 is equal to 0. You can check your calculator. Sure, we'll do it in front of you there. ln of 1 is equal to 0. Or like say e to the power of say 5.6. So 5.6 is sent to 270, and the log of 270 up to rounding error will bring you back to around 5.6. So this is what this means. Okay. And now what are we looking at? So it says, so basically what you can do, if y is log of x, do the exponential of both sides, you get e to the y, and then because log and exponential are inverses, if you do log and then exponential, you just go back to x, you end up with this thing. And then you can do implicit differentiation to this. Okay, so let's look at this. So again, as usual, write y as y of x. Now, there's a lot of technical maths here. For Math 6040, I just want you to home in on this actual question. Use implicit differentiation to find dy dx. This is your implicit curve. I just want you to think like that. So you write y as y of x. So you get x is equal to e to the y of x. That's all. That's all. Now what we want to do is differentiate both sides with respect to x. So the derivative of x with respect to x is 1. Now, e to the y of x needs a chain rule because you've got an outside function which is e to the x and an inside function which is y of x. So we'll differentiate the outside function. What is the derivative of e to the x? Now you can go and look in your tables, but I've just told you up here that the derivative of e to the x is itself. That's what e to the x essentially is. It's the function that you differentiate and you get the same thing. So differentiating the outside function e to the x, you get e to the x. But the chain rule says don't evaluate at x, evaluate the inside is y. And then the chain rule says multiply by the derivative of what's inside. So multiply by the derivative of y of x, which is dy dx. And now to solve this for dy dx, you just need to divide both sides by e to the y. So you end up with, and swapping sides around, dy dx is 1 divided by e to the y. So chain rule, yeah, scary, but not too bad. Then part B says, hence use e to the y equal to x to write down the derivative log x in terms of x alone. So this actually is very easy. Dy dx is equal to 1 over e to the y, and it says use e to the y equal to x to get 1 over x. Now if you're kind of going, what? Well, you need to realize, what did we start with? Y is equal to log of x, and we've shown that dy dx is equal to 1 over x. Now that's in the tables. The derivative log of x is 1 over x. Where did it come from? This is where it came from. Now in fairness, I'd like you to engage with the theory, but you can actually answer the questions here without being too deep into the theory. Okay, we'll do another question. Consider the function y equal to x to the x. Now this thing is called, what we do here is actually they call logarithmic differentiation, but it's spoken through with you. Like, how could you differentiate x to the x? Let's see. So this is the question. Take the log of both sides to show that this is the case. Now this involves you knowing about stuff about logs. If you don't, you can still do the rest of the question. Okay, so take the log of both sides. This is the thing here. We're going to take the log of both sides to show this. So we're going to take log of y equal to log of x to the x. Now, I don't know how much you know about logs. One of the things you can do when you're a bit stuck is look in your big tables, and one of the things that you'll see in the big tables is that log of a to the x, so I'm not sure exactly how it comes out in the tables, but one of the properties of logs is that it turns powers into multiplication. So instead of to the power of x, it's multiplied by x. This is in the big table. So you end up with log of y is equal to, so instead of to the power of x, multiplied by x. And that's step 1. Okay. We've shown that log y is equal to x log x. And I can still do the next bit even if you couldn't do that. Hence, now hence means using what you just did, use implicit differentiation to find dy dx in terms of x and y. Now if we do implicit differentiation to this, once we find dy dx, that is the derivative of x to the x. And by the way, I don't know any other way of finding the derivative of x to the x. X to the x is a weird kind of, well, weird function, yeah. Like 3 is sent to 3 cubed, 7 is sent to 7 to the power 7. It's a very fast growing function. Anyway, so as usual, if you're doing implicit differentiation, put y as y of x. So you got log of y of x equal to x times log of x. And we're going to differentiate both sides with respect to x. Log of y of x, this is an outside and an inside. This will need the chain rule. And the chain rule says differentiate the outside. The outside function here is log of x. The derivative log of x, well, that's handy, we just saw it, is 1 over x. So it's 1 over x. The chain rule says evaluate at the inside. The inside is y. And then times the derivative of what's inside. And the derivative of y of x, well, all you can say is that it's dy dx. Okay, that's differentiating the left-hand side. Now, what about x times log x? Well, you have to say, because it's multiplied, it is a product rule, and we'll do a product rule. So the product rule said it's the first thing by the derivative of the second thing. The derivative of log of x is 1 over x, plus the second thing, which is log of x, times the derivative of the first thing. The derivative of x is 1. And now what we're going to do is we're asked in this question to find dy dx in terms of x and y. All we have to do is multiply both sides by y. Now x by 1 over x is like 2 by a half, 3/3, 4/4, 5/5, 10/10. This is equal to 1. Log of x times 1 is just log of x. So I have y, if I multiply, oh yeah, let's slow down for a second. I've got divided by y. That's what 1 over y is. It's divided by y. I want to undivide by y. What is the inverse of dividing by y? Multiplying by y. Okay, so that will get rid of that here, and then I need to multiply this by y. I get y times x divided by x, we said, is 1 plus log of x. That's implicit differentiation. That's not much good for, oh, the derivative of x to the x is, what's the y doing there? Ah, y is equal to x to the x. So what you find is dy dx just says substitute y equal to x to the x into the previous part. So I just substitute in y equal to x to the x to show that the derivative of x to the x is this little thing here. Okay, so that is implicit differentiation.